Hi, my name is Lukas, and today I'm talking about Pauli strings and Pauli transfer matrices. So the first part we talk about is Pauli matrices or Pauli strings. The Pauli matrices together with the identity the X Pauli matrix, the Y, and the Z. And for notation, we introduce these labels. So we say sigma 0 is the identity, sigma 1 is X, sigma 2 is Y, and sigma 3 is the Z Pauli matrix. And the first thing that we need for the Pauli strings or the Pauli decomposition is that those four matrices form a basis of the 2x2 matrices, and they also form an orthonormal basis with respect to the scalar product defined by scalar product of A and B is equal to the trace of A dagger B. With those Pauli matrices, which are used for single qubits and the unitaries there, we also introduce Pauli strings which act on multiple qubits. So we have for the label set, which goes from 0, 1, 2, and 3, we take the n-fold product. So we look at strings of the form, for example, 0, 1, 0, 2, 3. So we have n copies of the labels, and this string corresponds to taking the tensor product of Pauli matrices. So here we have the 0, tensor the sigma 1, tensor sigma 2, tensor sigma 3. We can also write this in a different way as identity tensor X, tensor Y, tensor Z. And also, if you want, you can just do indices on the positions where they act. So we can also write X2, Y4, Z5. Those are like the different representations that we have for the Pauli strings. As for the single qubits, the Pauli matrices, we know that all these Pauli strings form a basis of the 2 to the n times 2 to the n matrices. When we represent the Pauli strings in the usual tensor basis, then if we have, for example, sigma z tensor something, then we have this kind of product or block structure where here we have 1 times the rest, here we have 0 blocks, and here we have -1 times the rest of the Pauli string. And the same holds true for all the other Pauli matrices. So if we have the Y in the first component, then we would have just blocks here, and those blocks would be 0, and alike for all the qubits. So this thing goes recursively. One thing that you can do with these Pauli strings is use that they form a basis. So you can express matrices in the basis of Pauli strings. So for a given matrix, say A, we want to decompose it as a sum of all the Pauli strings of length n, and they have a weight as a scalar factor and the corresponding Pauli matrix, or the matrix corresponding to that Pauli string. And the first naive approach to calculate those weights is to, say, use the scalar product. So if the weight is equal to scalar product of A and the Pauli string. So this approach is very costly because we use the matrix multiplication and we do a trace afterwards. And so there are a lot of techniques that try to optimize that, calculating the trace and the product of the matrices. The approach that is used for the tensorized Pauli decomposition is the observation that we had just before, where we know that there is this kind of block structure. So for all Pauli strings that have sigma z in the first entry, we know that this has the block structure. And with that in mind, we define the so-called cumulative matrix weight. So we say that omega t and the star stands for all the Pauli strings that are not evaluated yet. And that is the trace of the first qubit of sigma z, or sigma t, tensor identity to the n minus 1. So we only have the Pauli matrix in the first part times the matrix that we had before. So the matrix we want to evaluate the cumulative matrix weight from. But these cumulative matrix weights can be calculated recursively. So if we compute, for example, for z and x, then we first do that from that with z, and from that cumulative matrix weight we form the next cumulative matrix weight with the x. And if one of the cumulative matrix weights is 0, then we can sort of get rid of this branch and just do computation for the other cumulative matrix weights. This scheme, or this kind of how to do computation, can be used for a lot of things, like multilinear maps, when you have a tensor product of maps, or if you have basis for tensor products, just as in this case, where we have the Pauli basis for each tensor factor. And there's also an application where it's already been used, this kind of technique, in the Q-hipster algorithm, where they have single qubit gates in parallel. We know that in each step, or in each recursion, we have 4 to the I possible Pauli strings, and the size of the matrices scales as 4 to the n minus I. So in total we have n times 4 to the n runtime. And this is also a runtime that other algorithms got. That now leads us to the algorithm, how it's performed. So in each recursion step, we do first calculate all the cumulative matrix weights for all the Paulis. Then we do the recursion, so we calculate the TPD, the Tensorized Pauli decomposition of those cumulative matrix weights. And in the end, we collect the output as a vector and do that, insert that into the one above, like the level above. And if we are at 1 times 1 matrices, then of course we just output the entry. Now we talk about the Pauli transfer matrices. The Pauli transfer matrices are a tool that can be used for quantum channels and also for operations on matrices. So we are now dealing with, for example, density matrices. So we have 2 to the n times 2 to the n matrices, which stand for density matrices on n qubits. For example, we now consider a map F that maps a density matrix to another density matrix. And this map that we consider should be linear. Now that we have a linear map, we can represent it in the Pauli basis, which is what we talked about before. So we can write that as a matrix. So we have rho represented as the Pauli weights. So we get those weights we defined before, those omega t, as a vector. And applying that map now corresponds to matrix multiplication like this. We view that as a vector and we do matrix multiplication. So with the Pauli transfer matrix of F, summing over the first index with the input and getting a result which is F of rho, and there the Pauli weights of that output. One example for that would be quantum channels, which are positive, completely positive trace-preserving linear maps on the operators of a Hilbert space. But of course we deal now with qubits, and so it would be 2 to the n times 2 to the n matrices. And there are a lot of representations available for quantum channels. For example, the superoperator representation, where you do basically the same thing. You write down your input matrix as a vector. For example, in doing columns first and then the rows. And you do the same kind of thing with matrix multiplication. So your quantum channel would correspond to a matrix. There's also the Choi representation. You associate to your channel a matrix, which is defined to be sum over I and j. And we do here the tensor product of a matrix with just a 1 on the ijth position, tensor product with the output of that channel of that matrix. And here there's also a relation to the Pauli transfer matrix, where you can read off the components, or you can read off the output of the Pauli transfer matrix by doing a Pauli decomposition on the first ones. Another way to represent quantum channels is the so-called cross representation, where you have that rho maps to the sum over cross operator I product with rho and the adjoint of that cross operator. And a similar kind of structure we have for unitaries. We apply unitaries to density matrix in that way. To calculate the Pauli transfer matrix for such a map, such a linear map on the density matrix, density matrices, we use that we can write those operators on the left and right as the sum over the Pauli matrices of sigma t tensor product with the cumulative matrix weight. And so if we now want to evaluate the action on some Pauli string, so we say rho is equal to sigma s tensor sigma s prime and so on, then we can do that again in a way that respects the tensor product structure. So we have sum over t, sigma t tensor omega t star multiplied with this Pauli string multiplied with the adjoint, which would be sum over r sigma r tensor product with the other cumulative matrix weight. And we can now sort of separate the first qubits from the other qubits. So that in total we have sum over t and r, sigma t tensor, sigma t, sigma s, sigma r. Sorry. There. This one is of course adjoint because it's the second operator here. And the adjoint of the Pauli matrix is itself, as we know. And for the second tensor factor, we have the conjugation with the cumulative matrix weights. And so this also reproduces the same kind of pattern where we do the Pauli, where we calculate the Pauli transfer matrix for the first tensor factor, and for the other ones we do it recursively and then take just the tensor product of the Pauli transfer matrices. Another situation where we use Pauli transfer matrices is in the time evolution. So for example, we have for density matrices the following equation. Where we have the commutator with the Hamiltonian. If we have a different kind of time evolution with Lindblad operators, then we might consider a term where we have the anti-commutator with rho, with the density matrix. We also have the same way to compute that iteratively, because there is a cool formula that relates the commutator of a tensor product to commutator and anti-commutator of the tensor factors.
Thank you very much for your talk on Tensorized Pauli decomposition. And I have some follow-up questions.
Yeah.
How do you deal with the exponential cost of the algorithm?
So that's like a standard thing that everybody has when simulating quantum things on a classical computer, because if you do n qubits, then you have a scaling that goes to the power of n, no matter what. And so the only way to deal with it is basically to reduce the constants or to reduce the basis in the exponential growth. So one example would be that other algorithms have a base of 64 to the n, and we have just a scaling of 4 to the n, which reduces the runtime by a lot.
And can you tell us something about the competitors in the field?
Yeah, so it's a cool thing that a lot of people look at those Pauli decomposition problem, and they try to find those algorithms that are faster than the others. And so there are a few competitors that we have, and I think one of them already has beaten us. So it's a cool race to the top.
Oh yeah, that sounds really cool. What did you enjoy the most while working on this project?
So one thing I enjoyed is that I worked with Lennart and Sabhyata, so we worked in a team, and they always helped me when I had problems and the other way around. And for me personally, it was very cool to kind of get to know the structure of this, like how do we formulate this in mathematical terms and how can we visualize it and how to get an intuition on those Pauli strings and the Pauli decomposition.
Thank you very much again, Lukas.
Yeah.
And we are looking forward to your next talk.
Yeah, thanks.